Hello all. In today's session we will continue basic components of CNN. So in the previous session we have talked about the components. We have discussed the three components of CNN. The first was the convolutional layer, second was called as the pooling layer, and the third component is fully connected layer. In the previous session we have talked about how convolutional layer processes the image and then generates a reduced dimension of the image. And also we have gone through the hyperparameters which are present, which controls these convolutional layer. Let us continue with those hyperparameters. So these were the hyperparameters, and these we have already discussed about filters and kernel size as well as stride. Let us continue with the strides, which is also called as step size, and the stride value will be either 1 or sometimes 2 also. It can be 3, but this is not in common practice. And this is the formula to find out the size of the output feature map, also called as activation map, also called as convolved image. This is the formula used to find out the shape, where input size represents the size of the image. This is the size of the kernel or filter, and the stride value plus 1. For example, if the image is a 5 by 5 image, the kernel what I am using in the convolutional layer is 3 by 3. This will be the featured map which will be generated, which is of size 2 by 2, which is formed, the value this 2 by 2 will get from the formula as the image size minus kernel divided by the stride. Here what I am using is 2 plus 1. This will be equal to 2, which gives a 2 by 2 featured map. So when I am performing the convolutional operation of 5 by 5 image with 3 by 3 kernel with stride as 2, I will get a featured map of size 2 by 2 using this formula. And how did I get this is, this kernel will be placed on the image, and dot product of 1 into 0 plus 0 into 1 plus 9 into 0, all these values we find the dot product and find the summation, which will be equal to 51. And how do I get 22? By using the stride size as 2, I will shift this kernel on the image 2 positions towards the right. So this is the first position, this is the second position. So this is, I will place my kernel here, perform the convolution operation of 9 with 0, 3 into 1 plus 0 into 0 plus 0 into 3 and so on. I will get 22. Similarly, this 55 value, how do I get? When I place this filter 2 units, when I shift 2 units down and place the filter here, which is of 3 by 3 size. So 5 into 0 plus 3 into 1 plus 8 into 0 and so on. I will get this 55 and 56. This is the way how we reduce the size in a convolutional layer using this stride value as well as kernel. Coming to the fourth hyperparameter, which is called as padding. Padding, also called as zero padding, because we will add zeros around the border of the image. Now why do we go for padding is to preserve the spatial dimensions of the input image. We make use of padding. Now what do you mean by spatial dimensions is, in the previous slide we have seen that a 5 by 5 image with a 3 by 3 kernel and stride size as 2, 5 by 5 image got reduced to 2 by 2. That is, the original image is 5 by 5. When convolution operation is performed with all these parameters, I got the image reduced to 2 by 2. So there might be a possibility of a reduction in the spatial size, or there might be a possibility of missing some features or corners or edges of the images. So to avoid this reduction in the size of the image, we go for this method called as padding. So you can see here this blue box represents my original image with all the pixel values, which is of size 4 by 4. And when I add padding with 2, that is, I will increase the height and width with 2 by adding zeros. So my 4 by 4 will convert into a 8 by 8 matrix. And this is what in the coding we are using as padding is equal to same Now what does this padding is equal to same means? The size of the input image should be same as the size of the output image when I use this command as padding is equal to same. That is, my input size is 4, then the output which is generated also should be of 4 by 4 matrix, and padding is equal to same means apply padding to the given image. You can also have another option as padding is equal to valid, and when I use this, no padding is used. That means I will reduce the 4 by 4 image by applying the kernel and stride size. Here no reduction in the image, input and output image are of same dimensions. Here the image dimension gets reduced. So to preserve the spatial dimensions, we make use of padding. So what you need to remember here is the two hyperparameters what we have discussed, that is the stride and padding, are meant to control the behavior of convolutional layer, as well as they also control the size of the output also. That is, they decide whether to pass the entire image or to ignore some of the features of the image. And this is the formula when I use padding. This is the formula to find the size of the feature map. So this is an example here. Original image of size 5 by 5. I am adding padding here. Padding is equal to 1. That is increasing the height and width by one layer by adding zeros. And the kernel size what using here in the slide is k is equal to 3, and let the stride size be 1. So when I substitute these values in the formula, h is equal to 5 size of the image plus 2 into along height I am increasing by 1, and along width also I am increasing by 1, minus k is the kernel size by s is stride. By substituting these values you will get 5. That means my convolved image or feature map size is 5 by 5, and the command what we have used is padding is equal to same. That is, the input image, original image is of size 5 by 5, and the convolved image or feature map what we got is also 5 by 5. There is no reduction in the dimensions of the image due to this padding method. How did I get these pixel values here? By sliding this filter on the image with a step size of 1. So first I will place this 3 by 3 filter on this, perform the dot product and summation, I will get this value. Next stride is 1, so I will move one position towards the right to get the next pixel value, that is this pixel value, and so on. And how do I get these values? By placing it one position towards the bottom, that is shifting one position towards the bottom. Why? Because our stride size is 1, I'll get this minus 11 value and so on. So the output feature map shape what we got is 5 by 5. So next we will talk about the second component of convolutional neural networks or CNN architecture, which is called as pooling layers. So when we add more convolutional layers, it will increase the depth of the output layer, as we have already discussed in the previous session. As I am increasing the number of neurons in the hidden layer, the depth of MLP model increases. Same is the case with CNN. As I am increasing the number of convolutional layers, the depth also increases, and as the depth increases, obviously the number of parameters also increases and the model becomes more complex. Why? Because the model has to learn all those parameters which got increased due to increasing the number of convolutional layers. So adding convolutional layers will increase the complexity of the mathematical operations also. So due to avoid those complexity in mathematical operations, this pooling layers is introduced. The other name for pooling is subsampling, which will help to reduce the size of the network by reducing the number of parameters which are passed to the next layer. So you can see here, after each convolutional layer, I am applying pooling layer. You can also have two convolutional layers and one pooling layer after two convolutional layers also, and this is the command to call the pooling layer, max pooling for two-dimensional data, and syntax is pooling size I'll mention as 2 by 2, and the strides what I'll use is 2 in this example. So there are two types of pooling. The pooling operation, as I said, it will reduce the number of parameters. That is, it will resize the input image. That means as I said that we have two main types of pooling layers. The first pooling layer is max pooling, which will find the maximum value of the pixels. Now when I say 2 by 2 pooling filter, this is my original image, and when I say 2 by 2 pooling filter, I will place my filter here, and the max of 1954 is 9, and using the formula, the original image uh, size is 4 minus pooling filter size is 2 divided by stride size is here mentioned as 2 plus 1. So this will be equal to 2. That means my feature map is of size 2 by 2. And as my stride size is 2, I will shift the second filter 2 positions towards the right, and the maximum value of the pixel here is 8, and so on. This is called as max pooling. It reduced the 4 by 4 image to 2 by 2 image. Coming to the second type, average pooling. Same here, as we are finding the maximum value, this pooling method will find the average of all the pixel values in each receptive field. And the point what you need to remember here is the size of the image reduces, but the number of layers will remain as it is when we perform convolution. You can see here in the diagram, I have a convolutional layer of size 4 by 3. Sorry, 4 by 4 by 3. That means I have 3 layers, 3 convolutional layers, each of size 4 by 4. And this 4 by 4, how did I get size? By applying some, I am using some image. For example, I have used an image of 5 by 5, applied kernel of some size, and stride value as 1. Substituting in the formula, I got my image got reduced to 4 by 4. And the number of layers what I am using here is 3 layers. So when I am applying pooling layer, I will have all the 3 layers, but there will be reduction in the size of the image. The number of layers will remain as it is. Next, we will talk about another type of pooling called as global average pooling. Now, what is this global average pooling is? It is more extreme type of dimensionality reduction, we can say, because instead of setting a single window, it will calculate the average value of the entire pixel or of the entire feature map as shown here. Among all these pixel values, it will find the average of all the pixel values and will generate a single pixel value in the feature map. Now, why do we go for pooling layer? Why is it important to reduce the dimensionality? I can say that pooling layers will reduce the dimensionality. But why is it important to reduce the dimensionality? Because when we go for some complex operations or complex projects, the convolutional neural networks will contain many convolutional layers, and each layer may have tens and hundreds of convolutional filters called as kernels. Since the kernel contains the parameters, then the network have to learn all those parameters. That is, the network has to update all those parameters. So by adding the pooling layers, the important features, it will decide whether to pass that important feature or shrink the image and pass the important feature. So pooling will reduce the image resolution but keep the image important features as it is. So you can call this pooling as downsampling. So think of pooling layer as an image compression program which will reduce the image resolution. So this is the visual representation of how the output we get after convolution. This is the first figure represents after convolutional layer 1 and 2. This is after pooling layer and combination of both convolutional and pooling layer. So this is the recap of the coding what we have told or discussed now. And similarly, as we talked about pooling also, this is the coding used for pooling. And the output what we get from the pooling layer, that is convolutional layer output is given to pooling layer, and pooling layer output will be placed in a flattened box. That is, it is flattened and then given as input to a fully connected layer. You can see here, these are the features which are extracted That is the output of pooling layer. Any number of pooling layers and convolutional layers you can use. And what do I notice here? I have 5 by 5 by 40. That is, I have 40 layers here, each of size 5 by 5. And this will be converted into a one-dimensional data, that is 1, n size, 1, n. This n represents 5 into 5 into 40, which is nothing but 1000. So the output of the pooling layer is flattened and given as input to the fully connected layer, which makes use of softmax function, which find the probabilities of the given image belonging to any of the 10 labels. So this is the end of all the components of convolutional neural networks. Thank you all.